Hi there folks, today we're talking about ratios and proportions. And so the first thing we're going to look at here is ratios. Ratio is just a comparison of two quantities by division or two numbers by division. And really there's a couple ways to express this. You could express it this way as like 1 to 3, or you could express it as the fraction is the most common for us, like 1 to 3, or in terms of words, 1, 2, 3. The most common of which, they all mean the same thing. They all mean we're kind of dividing these two things. We're comparing them with division. The one we're going to use the most often is the fraction version of this thing, okay? So we'll typically use the fraction. You'll see it expressed in other ways, but as soon as we start to do the math with these things, we're going to want the fraction version, okay? So, for example, this one, it says the Washington Monument is 550 feet tall. A replica of the monument is 18 inches tall. What's the ratio of the replica to the full-size monument? And the way that's worded is kind of important because we want replica to the full-size monument, so we want replica first and then the full-size monument. In other words, we want, you know, the replica in the numerator and the full-size monument in the denominator. And there's a couple of things to consider here. You know, one of the things we look at, like if we were to just compare this the way it is and say something like, okay, that's 18 inches compared to the 555 feet. And then from there we could reduce that thing. The problem with this particular comparison right now is that these are not in the same units. Okay, so we could reduce this thing. Let me do that real quickly. So if I divide each of those by 3, it looks like I get a 6 inches compared to 185 feet. Okay, and so that is still a ratio. We're comparing these two things by division. But the problem with this ratio, and we will see ratios that are like this where there's two different units, is that it's really hard to simplify this completely because we're going to be stuck with those two units in there no matter what. Okay, so another way to do this, a nicer way to do this, is to first make sure that we have the same units for these things. And so right away I could look at this thing and say, okay, the 555 feet, let's convert that, and I'm just going to use my factor label here. So I want to go from feet to inches so that I have a better comparison with these two things. And so right here there's 1 foot is 12 inches, and then from there I multiply this out and I get 6,660 inches. The units cancel. And so once I have that, now I can set up a new ratio here, and I can say, okay, now my ratio is 18 inches compared to the 6,660 inches. And what's nice about this is because they're the same units, the units actually cancel. And now I can reduce this fraction. When I reduce it, it reduces to a 1 over 370. And so now it's easier to express the ratio because I don't have to worry about units being pulled in there, okay, because I've changed them to being the same thing. So that's one version of this thing. And really, I went the route of inches here. I could go the route of feet instead. Like I could convert the 18 inches to feet just to show you real quickly. So inches to feet here. So again, 12 inches is 1 foot. And of course, I cancel out the units, and I multiply and divide and everything, and it ends up giving me a 1.5 for the feet. And so if I set this up the same way, it's still, the replica is now 1.5 feet compared to the full-size monument, with its 555 feet. And when I reduce this, it still gives me 1 over 370. And so the point I'm trying to make there by showing you each of these is what's nice about when we convert it to the same units is it's more universal. It doesn't matter which units I'm using, I'm going to get the same ratio no matter what. If I were to go ahead and convert each of these to centimeters, which would be ridiculous of course, and then found the ratio, I'd still get 1 to 370, so that ratio would remain the same. Okay? And so by converting it to the same units, we get this more universal ratio for this thing. Okay? If I look at something like this guy using a ratio to find some values. So here a fundraiser is selling milk chocolate and dark chocolate candy bars. The ratio of dark chocolate to milk chocolate should be 3 to 5. If the plan is to sell 240 candy bars, I want to know how many of each are needed. All right? And so the thing here is, you know, right away when we go to set up this ratio, we want to start thinking about like 3 to 5, but we don't have either of those values. The ratio I instead want to think about, because it gives me the total number of candy bars, so let's think about this split into two ratios. If you think about the candy bars in terms of dark chocolate versus the total, it would be 3 to 8. And for the milk chocolate versus the total, it would be 5 to 8. And the reason that's a nice ratio is because I have one of those values. I have the total. So if I want to say, okay, the ratio is 3 to 8, in other words, 3/8 of the total should be the dark chocolate, and 5/8 of the total should be milk chocolate, I can now find the milk chocolate and the dark chocolate by saying, okay, 3/8 times the 240. And that'll give me the number of dark chocolate, which ends up being 90. And then I can say 5/8 times the 240. And that'll give me the number of milk chocolate, which is 150. So 90 dark chocolate candy bars and 150 milk chocolate. Okay, so by taking the ratio and switching around, because there's, you know, the ratio of milk to dark chocolate, but then we can convert that to a ratio versus the total, which allows us to kind of multiply this thing out. Okay. An extended ratio is really just kind of what it sounds like when we kind of tack on another ratio to compare with these things. All right. So in an extended ratio, we're comparing 3 or more numbers. So in this one, it's A to B to C. And what that allows us to do is it kind of allows us to break this down into a bunch of different ratios. So like if I have A to B to C, it means that I could use just that one ratio of A compared to B. I could use this back ratio of B compared to C. Or I could use kind of this bridged ratio from this guy to this guy and compare A directly to C. Okay? And so we kind of have this nice setup of a bunch of different ratios being compared, and that's what an extended ratio really gives us. It gives us a bunch of ratios that we can express simultaneously. Rather than having to write this as 3 separate ratios, I write it as one extended ratio. Okay? For example, if I look at something like this guy, it says the lengths of the sides of a triangle are in the ratio 3 to 5 to 6. If the perimeter is 90 inches, find the length of each side. All right? And so the first thing, of course, I'm going to do is I'm going to draw a picture. So I'm just going to draw this triangle off to the side over here. So here we go. Here's my triangle. And it says the ratio is 3 to 5 to 6. So the shortest side is the 3. And then I'll call this side the 5 and this side the 6. So now that's just a ratio when I compare these things. Like, you know, when I compare these top two sides, I would put the 3 over 5. But keep in mind, like, if I made this side a 6 and this side a 10, you see that I would have the same ratio because I would do 6 over 10, which would reduce to the 3 over 5. So essentially, any multiple of 3 and 5 would work here, as long as I use the same multiple of 6. So really what it's expressing then when I think about the ratios is it's saying it's going to reduce to that, which means this could be 3 times some value if this is 5 times the same value and this is 6 times the same value. All right? And so this is the situation we're in. Well, now that I have those ratios, I want to know what the actual length of each side is. So I need to know what that multiplier, what that x value is. So then I can just say, okay, well, the perimeter, the 5x plus the 3x plus the 6x, has to equal the 98 inches. And now I can just solve for x. This gives me a 14x equals the 98. I divide each side by the 14, and I get x equals the 7. All right? And so I found x, but it asked me for the length of each side. I got to plug that thing back in. So this is 35 inches. This one up here is 15 inches. Or sorry, 21 inches. I just plugged a 5 in like a crazy person. And then the last one down here is the 42 inches. Okay? So again, because it's a common ratio, we could have multiples of these things, so you have to find out what that multiplier is. All right? And then the last thing we're going to look at is proportions here today. And proportion is really just when we're setting two ratios equal to one another. All right. So an equation in which two ratios are set equal to one another. A couple ways to express it. If we're expressing it in our kind of fraction notation, it'd be like A to B equals C to D. Or expressing it in this in the notation using the colons here would be A to B equals C to D. And hopefully you can see that each of these means the same thing. The difference is how you approach solving these. When we're in the fraction format, we're going to use cross-multiplying to solve. Okay, and if you remember cross-multiplying, remember you just take this, the numerator times this denominator, and we write it here, so that would be CB, and this numerator times this denominator, and we say that equals AD. Okay, and so that's how cross-multiplying works. If we're in the other format, we're going to do the extremes and means where we multiply them, and we kind of set it up the same way. So if you look here, the extremes are the A and the D, so I do A times D equals, and then the means is the B and the C, so I say equals B times C. And really it's the exact same thing, it's just the approach we take when it's in that specific format. Okay, it even gives me the same values, the AD equal to the BC. And keep in mind, it doesn't matter that I have CB written in one and BC written in the other, or that I have the symmetric property being used here. It's giving us the same thing when we cross-multiply versus doing the extremes times the means. All right, so just be aware of that. Most folks, instead of doing the extremes times the means, will just rewrite this format over here. They'll rewrite this guy in this format and then cross-multiply, because that's what we're familiar with. And if you want to do that, that's fine. Okay? So here we go. If we take a look at something like, sorry, I scooted my screen around a little bit there. If we take a look at something like the next guy, again, it's in that format of you know, just fractions. So we're just going to cross-multiply. So I do the 5 times the x, and I write my answer down here. So that's a 5x. Equals, the equal sign just kind of stays in between, so now I do the 6 times the 4, and I write my answer down here. That's a 24. And now I can solve this thing. I divide each side by the 5, and I end up with x equals, oh, we'll just do a decimal here, 4.8. Okay. The next one, the same kind of thing. I do y times the 9, and I write my answer down here. That's a 9y. The equal sign just kind of tags along for the ride, and then I do the y plus 4 times the 3. And that's my distributive property. That's a 3y plus 12. Okay. And now I subtract the 3y. That gives me a 6y. And now I divide by the 6, and I end up with y equals 2. And then the last one, again, either convert this to the fraction form and then do your cross-multiplying, or, again, look at it in terms of the extremes and the means. If I look at the extremes here are these guys. They're the ones on the outside. They're the extremes. And I just multiply those. That gives me a 15m equals. And now I do the means, which are the ones in the middle. The means, get it? So when I multiply those, that gives me a 3m plus 3. And now I can solve the same way that I always have solved. Okay, I subtract the 3m. That gives me a 12m. And now I divide each side by the 12, and that gives me a 1/4. Okay? So again, if you're uncomfortable with the extremes and the means, convert this thing to the fraction form and then just cross-multiply. All right? The last thing we're going to look at with our proportions is some of the properties of proportions that we have. We can rewrite some of these things. For example, if I look at something like this guy, I can flip each fraction as long as I do it to both fractions. So if I have a over b equals c over d, I can rewrite that as b over a equals d over c. All right? And the reason this works, we'll do kind of like a little mini proof of each of these over here. If I do just a little mini proof, if you cross multiply, and that's what this first step is going to be, if I cross multiply, I get AD equals BC, all right, or CB, whatever you want to call it. And now from here, I can divide by whatever I want on each side. If I divide each side by AC, you see over on the first side, the A's are going to cancel, and I'm left with D over C. And on the second side, the C's are going to cancel. I'm left with B over A. And of course, I can switch the order of that and say, okay, B over A then equals D over C. That's where this comes from, all right? So be aware that we're allowed to do this. That's why we're allowed to do it, okay? If I look at the next one is basically telling me that I can switch either of these two diagonal pieces, okay? So right here, I'm switching the B and the C. Okay, so I can make diagonal moves by switching two of these things, and that's what I've done here. I've switched the place of B and C. And again, the reason I'm allowed to do this, if I take it off to the side, if I start here with AD equals CB, and again, that's just from cross-multiplying, or BC, whatever you want to do there. That's just from cross-multiplying. Again, I can divide each side by whatever I want. So if I choose to divide each side by CD this time, that first piece, what's going to happen is it's going to cancel. The D's are going to cancel. I'm going to be left with A over C. The second piece, those are going to cancel, and I'm going to be left with B over D. And so now I'm in that situation where those diagonals have switched, and I match this guy right here. Okay? So just showing you why this thing works so that you can use these moving forward. And essentially, I'm just kind of, it's like I'm doing a little proof for each of these. The last one here, really, this is probably the one that's the most complicated for students, but it's basically saying that, hey, I can take the denominator and add it to the numerator of each of these. So like the first one is A over B, I can add that B to the numerator as long as the C over D, I add the D to the numerator, okay? So respectively, when you look at these denominators, here I have the B and here I have the D. If I add their respective denominators to their numerators, these things are still equivalent, okay? And again, I can show this starting essentially with cross-multiplying. If we start with cross-multiplying and I start with the AD equals the BC again, this one's a little bit weird because now what I'm going to do is I'm going to add the same thing to each side. Again, because it's an equation, I can do whatever I want, but I'm going to add BD, which is like the combination of the denominators. And when I do that, it leaves me with this. It leaves me with AD plus BD equals BC plus BD. And now from here, it's a little bit of factoring involved. So if I factor out the D over here, it leaves me with an A plus B. Over here, if I factor out the B, it leaves me with a C plus D. And now from here, I can divide each side by the same thing, and the thing I'm going to divide by is the dB. And what happens in that first fraction, hopefully you can recognize that those pieces are going to cancel. The D's are going to cancel, and it's going to leave me with A plus B over B. In the second fraction, the B's are going to cancel, and it's going to leave me with C plus D over my D value. Okay, and so that's where this thing stems from. That's a little overly complicated, but as long as you remember the properties themselves, again, you can flip each fraction as long as you do it to both. You can switch out diagonally, okay, so you can trade diagonally. And the last one is you can add the denominator to their respective numerators, and you'll still have equivalent fractions. Okay? And so just looking at some of these in action, like if I looked at something like this, if it gives me this proportion of x over 6 equals y over 7, and then ask me, okay, x over y would equal what? The property that's being used there, if I want to put a y where the 6 is, I'm essentially having to switch these diagonals, which means then this would equal 6 over 7. And what's nice about that is what's important here is now I have a ratio that involves all numbers, which can benefit me when I'm solving certain examples. Okay? The next one, again, same kind of thing. If you look at something like this, I've got d over 5 equals r over 10. And then what it's done here is it said, okay, 10 over r is going to be what? We're essentially just switching this guy, which means I have to do the same thing with the other. I have to switch this guy. Okay, if I flip one fraction, I have to flip the other fraction, so that's going to be 5 over d. And again, these are still equivalent forms then when I do this. Okay? And that's pretty much it. So again, when we're looking at these things, ratios, we're comparing by division. It's always best if we have those in the same units first before we simplify and find that ratio. We can set up multiple ratios from that to kind of work with our totals and solve for things. An extended ratio where we're just essentially extending that ratio to involve more values, and that essentially gives us more ratios that we can look at. And then a proportion is when we set the two ratios equal to each other. Again, solved by cross-multiplying or extremes and means. And then these properties of proportions where we can flip each fraction, we can trade the diagonals, or we can add the respective denominators to the numerators. Okay?